Happy day and welcome everybody. What we're doing today is we are talking about phase change diagrams compared to heating curves. And then we're also going to be talking a little bit about what are the effects of vapor pressure on rate of evaporation, on boiling point, on IMFs, on your heat of vaporization. So we're going to be connecting all of these and trying to draw relationships to all of these. Okay, so the first thing is that I want to talk about is the difference between the phase diagram versus looking at something like a heating curve. And so if we take a look, let's look at what our heating curve looks like. So let's scroll down to the bottom here. And we can see that on a heating curve, we've got temperature versus time. So this is temperature versus time. And we can take any substance. In this case, we've got water. And so we start as a solid, we go into a phase change. Then we've got only liquid, we go into another phase change, and then we go into the gas phase. And we know that if it's a pure substance, what should be true at the phase change? While it's phase changing, what's happening? The temperature is remaining constant. And so we can see that plateau where the temperature is remaining the same, okay? And so that is that's something that you're going to see often when you look at a heating curve. You'll see if you have a pure substance, you're going to see that. And during that point, remember, there are always two phases because it could be doing two things. For example, when we say where the boiling point is, for example, it could either be boiling at the boiling point, but what if the environment and the temperature surrounding was actually cooler than what the substance was? What would be happening? It wouldn't be boiling, it would probably be what? Condensing. Bless you. In that case, it should be condensing. So we have either boiling or condensing, and if something could be melting or what else could it be? So if the temperature around it was warmer, it could be melting, but what if the temperature around it was colder? It could be freezing. Okay. And I want you to keep in mind that the temperature surrounding is what it's going toward. So if the temperature, for example, was 50 degrees around it and it started off as solid ice, then it would start off as the solid, it would go to solid liquid, and then it would eventually become a liquid and then stop as a liquid if we ended at 50 degrees, right? But it would have to go through these phase changes. And while it is phase changing, we say that the energy is either used to raise the temperature or change the phase. Perfect. And so that's where we say it's either one or the other, and that's why we get the plateau. So the energy is used for one thing or another. Okay. Now I want you to take a look at a phase change diagram versus a heating curve. Okay. So in a phase change diagram, one of the biggest things is look at your axis. It's no longer temperature versus time. What is it? Yes. Now it's going to be pressure versus temperature. So we're not seeing that plateau that we were seeing before. So if you look for that plateau, it's gone. It's not there. Okay. This is still going to be for one substance. All right. And this is very, very typical. This is a very typical phase change diagram. This is not water's phase change diagram. Okay. Water's phase change diagram would actually be different from this. And one of the big things is, well, actually, I'll show you water in just a second, but it's the way that this curve goes. And so we're going to talk about the slope, whether this slope, the solid liquid line slope, is positive or if it's negative. Depending on where that is, that's going to determine if you have water or if you have almost every other substance that exists in nature. Okay. So almost every substance does this. Then there are other substances, well, actually, we'll get to that, may have a distinct phase change diagram like carbon dioxide. And what's funny about carbon dioxide? At room temperature, what happens to carbon dioxide? What do we know happens to carbon dioxide at room temperature? Perfect. What is that word? We start with an S, we say it sublimes. Good. It goes directly from a solid to a gas when we're at room temperature. You can get it to change into the liquid phase, but you have to be at the right temperature and pressure in order for that to happen. Okay, so let's take a look at this phase change diagram. So it says generally heating a solid will cause it to melt to a liquid, obviously, at the melting or the freezing point. And then continued heating produces a gas if you follow the horizontal line beginning at the pressure at 1 atm. Okay, so let's say that this right here was 1 atm. So let's just call this 1 atmosphere pressure. And if we were to go across the line, then I know that this here, it says, is solid. This is going to be in my solid state. And then what do you think this is then? Liquid. And then we're going to go over here and eventually get to the gas state. Okay. I know that this is temperature, and so this is you know, maybe this is 0 degrees, but we know that we're increasing our temperature. We don't know what substance it is. So we know that as we increase our temperature, we're going to go from solid to liquid to gas. Really easy to be able to remember that. So if you ever get a diagram or sometimes they ask you to sketch the diagram, then you know it's going to be solid to liquid to gas because it's a pressure temperature. So your lower temperature is going to be on the left. Okay. So then it says, if you follow the horizontal line, the substance begins as a solid, passes the normal what? What would we call this point right here? What would be happening to the substance? It would be melting. Very good. But because we're at 1 atm, we would call this the normal melting point or the normal freezing point. Okay? So the normal melting point. And so when we say normal, we're referring to sea level, which is 1 atm. Okay, so circle that. That's what we're talking about when we say normal. And then it's going to boil into a gas, and for most substances at higher pressures, the freezing, the boiling points are higher. Once boiling begins, the temperature remains fixed at the boiling point until all of the substance has what? Yes, until all of the substance converted into gas. Okay, and remember, the only difference between saying gas and vapor is what? If it's a vapor, normally at room temperature, it's what? It's a liquid. It's a liquid at room temperature, and then you would have to actually increase the temperature to get it to. But gas is the more general term. But if it's a vapor, that's when they use that term. Okay, I like to call it the Britney Spears effect because typically, I love Britney Spears, but typically she can only sing or she can dance. And so she would never, even when she was really young in concert, everybody knew it was one or the other. She wasn't doing both at the same time. Okay, thus at the boiling point, liquid and gas coexist in equilibrium. And so that can look like, well, I'll show you in just a second. Okay. The blank is the temperature and pressure which all three phases can exist in equilibrium. What do we call it if they all exist in equilibrium with each other? The triple point. Perfect. Okay, so the triple point is like a sunny day with slush. And you kind of see like a little bit of fog. So if you're looking out like on a lake, for example, and you see a little bit of like the fog with the water and the vapor state, and then you get the slush on top with the liquid and the solid mixed together, then that would be the triple point. All three phases can exist in equilibrium above the critical point. This is an important part. So if you take a look here, this right here is called the critical point. So there's our triple point, and that's our critical point. So the idea is that if I were to increase my pressure, then what happens to the molecules when you increase pressure? What always happens to the molecules? Yeah, they're going to come and they're going to end up getting closer and closer together, right? Expectation is that if the molecules get close together, what can you do to a gas? You stay at the same temperature, you keep your temperature the same, but you start increasing your pressure. Eventually, what's going to happen to your gas? Your gas is going to turn into a liquid. Okay? The IMFs are going to end up taking control, and they're going to say, we're so close, we've got this IMF, and then that's gonna make that connection, create that connection, that force between them, right? That attraction between them. And so then it's gonna form liquids. What do you think happens at the critical point? The temperature is so high that what? It's gonna stay as a gas. It will not convert into a liquid anymore. The temperature is so high. What do we say happens when you have a really high temperature? What's true of some average something? Average kinetic energy is really high. And so what happens is those molecules are like, you can't put us, we're not going to have an attraction to each other. We're going to be spread apart still. We are not connecting with each other. So above the critical point, your gas will no longer convert. Molecules are unable to, we're just going to say liquefy, or condense, or we could even say gas to liquid or condense. Okay, the blank is the amount of energy given off when a substance freezes, or the amount of energy the substance requires to condense. Actually, we're not going to use condense. We're going to say freezes or melts here. Let's do that one first, and then we can do the one when it liquefies. Okay, so let's change that to melts if yours isn't different. Okay, isn't the same as mine. Okay, what do we call that? It's called the heat of something. Perfect. The heat of fusion. The heat of fusion, which is delta HF, is the amount of energy given off when a substance freezes or melts. So what do we call it if it liquefies, if it condenses, or if it freezes? What is that delta H? It's called the heat of, good, heat of vaporization. The heat of vaporization, which is written as delta H vape. Perfect. So our delta H vape is going to be when it liquefies. Okay. So let's take a look here real quick before we look at water. Well, actually, we can even look at water's phase change diagram. You tell me, what do you notice is different about water's phase change diagram versus almost every other substance that exists? What's true on water's? What do you notice that's different about this phase change diagram? And we're not even going to look at specifics, just like at a glance. What do we see here? Oh, do you see this slope right here? That negative slope right there? That is very distinctive of, that is a that's water's phase change diagram. So the way that I do it is I say it's like water loves us, water, like we're, also made of water, right? So water wants to give you a big, huge hug. Okay, so water is going to give you a big, huge hug. And so you can see that this right here, being that this is like open arms, versus if it looks like this, which is almost every other substance where it's more closed, then that is going to be any other substance. Why does this matter? Okay. If we said that, for example, any other substance, I guess we can even take a look back over here for a second. If I increase the pressure, the temperature I'm going to keep the same, okay? Is there anywhere on here where if I increase the temperature, I can change a gas into a solid? Is there anywhere on here that you can see where I can turn a gas into a solid without changing the temperature? And you tell me, yes? I'm seeing yeses. Where? Where? Anywhere below this triple point. I like it. So if I say that my temperature is whatever this is, if I say my temperature is whatever this is, and I maintain the same temperature, and I go up, what is the green? What's the green representing? Gas. And I can increase my pressure, and I can turn it into a solid. Same thing here. I can increase, and I can turn it into a solid. I can increase, and I can turn it into a solid. Okay. I can also take a gas, and I can increase the pressure on a gas and get a gas to turn into a liquid. And that is just what we call condensation, right? So same thing. I increase my gas's temperature, and I can get it to turn into a liquid. Okay. So, but I want to ask this. Can I condense, or can I get my liquid pressurized or compress my liquid to turn it into a solid at any point on here? Can you see that I can turn my liquid into a solid? We see it? Here's my liquid right here. If I increase my temperature, I should erase this for just a second so that you can see this. Okay, so if I start here and I increase my pressure without changing my temperature, does my liquid change into a solid? Yes. Remember when we said that liquids are nearly incompressible? That's why. Liquids are pretty much incompressible because there's such a small range of temperature and pressure where you can actually get a liquid to turn into a solid. Okay, but it will happen, all right? So now let's take a look at water. Is there anywhere on here where I can get my liquid to compress without changing the temperature into a solid? Never. Never. There's nowhere on here where I can actually compress my liquid into a solid. So if we take a look at our phase change, at the actual, like what the molecules would look like, and remember this is all in theory, this is like if it were an ideal situation, what water would look like. So we've got these water molecules that are floating around in here. And then I'm going to decrease the temperature on it. And you'll see it on the phase change diagram where we are. And so this red dot is starting to move, and it's moving, 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 and eventually we're going to reach where the triple point is. And so now we're reaching the triple point right here, and then eventually it turns into a solid. I did that a little bit too fast, so let's go back. Okay, so here is like right around our triple point where some of them might be going into the gas phase, okay? And then I'm going to decrease and then now it is strictly just a solid. When we look at what it looks like, let's go back to water, what it looks like in the solid state versus the liquid state versus the gas state. So there's our gas, there's our liquid, and now watch what happens to the density when we look at the solid state. Which one is less dense? The solid state. There's more air inside of there, and so remember, density is just your mass per unit volume. And so if we just took one small region and then we weighed that, the molecules all weigh the same amount. It doesn't matter if it's solid, liquid, or in the gas state. So if I just cut out a little part right here and said I'm just going to look at this particular volume right here and how many molecules that I have inside of there in the solid state versus the liquid state, a lot more molecules in that little region, right? Versus in the gas state, then we're back and all spread out, okay, which is obviously the least dense. So water ends up being a little bit funny, whereas all the other substances, like if we do this for oxygen, there's our liquid state. So if I look at one small region right here, and then I go to my solid state, what happens? The density actually becomes higher. Okay, so for every other substance, they actually get closer together in the solid state. It's expected. But water, just because of the different IMFs and the way that the hydrogen bonds form with the water molecules, that's the reason why. Okay, all right. Okay, so let's fill in some of these blanks here. Make sure that you know subliming. Make sure that you know. So we're gonna go over those in just a second here. So same diagram for water shows the characteristic negative slope. This is really important. Okay, so remember that for essays. On the solid liquid equilibrium line, which accounts for why ice what? When it's in liquid water, what does ice do? It floats. The hydrogen bonds which form in liquid water make the liquid will be unusually what? Dense. I like it. It makes it a little bit more dense, even more dense than the solid is. Okay, looking at the graph upward from the temperature axis, one notices that increasing the pressure on a solid will change it to what? Well, that's the weird thing, is you can increase the pressure on a solid without changing the temperature. So I'm going to keep my temperature the same, and I'm going to increase the pressure. What can I eventually do to my solid? I can increase the pressure on the solid and turn it into a liquid. That's really weird. Okay, but that happens for water. So I can change it into a liquid. And the opposite effect of what occurs on the first figure, and then it says label the arrows. Okay, so we know, sorry, the arrows are supposed to be a little bit shifted over here, so let's just, we know that if we're going from a solid to a gas, we call that, starts with an S, ends with a G, we call that subliming, right? So this is going to be subliming. But then, what if it's going the other way? It starts with a D. Who knows? Good, depositing. So then that would be called depositing at that point right there. Okay, and then we know that this is obviously going to be liquid back to solid. So we know that's going to be solidifying or freezing versus the other direction would be melting. And then we've got water condensing, turning back into a liquid versus boiling, going in the opposite direction, across the line, obviously. And a lot of times I'll just call that the equilibrium line. And then this point here, what would you call that point right there if it's right at 1 atm? Normal boiling point. Very good. So that's going to be our normal boiling point. That's right there. Okay, and what causes water pipes to break when it's in freezing water? And so we know that what happens to the liquid water then when it turns into a solid? It can what? It can expand, right? So when it expands, when it's forming ice, causes expansion. So you can get that to burst. Okay. And the last thing that is down here that I wanted to show you is carbon dioxide, okay? And I want you to notice that here's 1 atmosphere right here. And at what atmosphere, what's happening? What's happening? We're well below the what? We're well below the triple point. Here's our triple point right here. We're very much below the triple point. And this is, if they ever ask you, which they do, I've seen this question asked about how carbon dioxide is different, that where the triple point is, that one atmosphere is actually way below that. And so when we're at our normal environment, then it would actually sublime. Okay, and so that's the difference between them. Okay, all right, and so last thing on here that I wanted to talk about too is going to be working out the differences between vapor pressure and IMFs and things like that. So happy day. I hope you enjoyed this video, and we'll be back to go over a little bit of the differences between the forces.